Welcome back everybody to our network principles section. In this particular video, we're going to be digging into IP operations. And as we dig into the IP operations, we really want to start breaking down and understanding the concept of the ICMP unreachable and the redirect. We'll be taking a look at IPv4 operations and IPv6 extension headers. We'll take a look and understand how IPv4 and IPv6 fragmentation works, the TTL or time to live value, IPMTU, and let's get started. So when it comes to ICMP unreachable, destination unreachable is generated by the host or its inbound gateway to inform the client that the destination is unreachable for some reason. That could be just for the fact that you can't ARP for it and you get a U message back in. A destination unreachable message may be generated as a result of a TCP, UDP, or another ICMP transmission. Typically speaking, depending on the situation at hand, there are multiple caveats for each one. A TCP may be because of the fact that your FTP times out and you get a TCP fin message back in or a reset. One particular situation I ran into recently, I found out that a ASA firewall could actually jump in and actually do send a reset bit in a TCP header to reset a half open or what they refer to as an embryonic TCP session, where you've gone, the host has contacted the server has gone back, but the host hasn't gone back to do the acknowledgement yet. So 2 out of the 3 parts to the three-way handshake are operational, but the key third part isn't there yet. That is one example of how that would come into play. UDP, you've got a voice issue, and then an ICMP transmission, you may be getting, hey, I can't get to this destination because there's an issue. There's a bunch of individual options and responses you can get back, and I'll show you how you can look those up. Unreachable TCP ports notably respond with the TCP reset than in destination unreachable type 3 as might be expected, because of the fact that you're dealing with the TCP transmission and not an ICMP packet. So it could be the fact that something in the data plane between the host and the destination interdicted and says, you know what? No, we're not doing that. It could be, typically speaking, if the protocol stack for that particular device is overloaded, which means that you could be breaching on a denial of service where there is just too many sessions trying to go to a particular host and it can't respond. That could be depending on the situation, and I want to be semi-careful here as how I explain this because I'm not a security engineer, nor am I a server engineer. But the TCP reset is typically handled by the interdiction of another device that says, you know what, I'm not sending the data through. I'm just going to reset the TCP session and drop it. I have seen this a handful of times in denial of service attacks where the end station just can't respond, and if it does respond, typically it's a firewall level issue on the device, and it blocks it and sends a reset message in favor of that, or a fin message sometimes as well. That's just my experience. I can't always explain why I see what I see, but typically speaking, in those situations, I wait for other teams to step in, take a look at it with me, and then we make a determination from there. And the last 2 times that I've seen it have been through a denial of service issue. Now, the error will not be generated if the original datagram has a multicast destination address. Now, multicast destination address is pretty huge because that technically should never be applied to a host. So a 224.0.0.0/4 address block should never be associated to an interface IP address. The two should not be the same. And the reason for that is because multicast destinations are designed for multiple end stations to communicate with, not to. Okay, so the idea here is, let's say for instance that there's a a video stream that you want to join, and you have an application, and that application is going to join a multicast group. A multicast group is basically just an IP address that the sender is going to point to as a destination address, and it's not an address that you apply to an interface. So it's not an address that is usable on an interface. It is a I'm trying to think of a good way, a good analogy to put up there. Multicast is obvious, but I would say probably the better analogy would be it's the address that the network is going to respond to. Remember, and the key thing here is multicast can be either link local or IP reach or network wide reachable. Link local simply means that it's got a TTL value of 1. It can't be routed between two interfaces on a router or a layer 3 device, because as soon as traffic comes in on an interface, hits the routing process, is switched, the routing process is automatically going to decrement at 1 from the TTL value total, and if only 1 exists, the traffic is going to get dropped because it can't be forwarded. So the multicast destination address is probably the best application for it, is actually applied to the network. Not a device, not an interface, but the network as a delivery mechanism. And the reason I say it that way is when you're dealing with it, it's really you're basically saying, you know what, I'm going to let the network get me to where I've got to go. And now what's actually interesting about that is the network, the end host could say, I want to join a multicast group. And then as soon as the last hop router that connects to the receiver, as soon as the last hop router receives that IGMP join message, he's going to flip that over to be a PIM join message if you're dealing with sparse mode multicast. And then that message is going to get forwarded up to the rendezvous point. And the rendezvous point is then going to know how to reach the sender. And both the sender and the receiver are going to join the same multicast group, which is basically going to be saying, okay, I want the network to build communication channels between the sender and the receiver, and that's going to be how they communicate. Now, with link local multicast, with your discovering your directly connected EIGRP peers or your OSPF peers, or LDP when we get into multicast or MPLS. Situations like those are going to be where the TTL value is set to 1. Now with routed multicast, which is what IP multicast is, that is a different situation, because then you're building a multicast tree, which are UDP flows, but in a I don't want to say a unicast direction, because it sort of is unicast, but I should say unidirectional would be the more appropriate term. The unidirectional in most cases from the source to the receiver. Now there is ways to make that bidirectional with bidirectional PIM. And we'll talk about that in CCIE. We're gonna not touch that in CCMP. But the idea is the network is going to be the destination, because the network is going to be the one that's going to be replicating the multicast flows from the sender to the receiver. The sender is going to send one message into the network, and the network is going to have to replicate that flow to any destination that wants to reach it, or the receiver, as it is commonly referred to. So multicast addresses are not viable or not allowed to be applied to an interface IP. If you try to type in a multicast address, it may take it, but it won't work. So that's one of the things that is very important for you to understand. Physical connection to the host does not exist, so that's where you might get these messages in play. The indicated protocol or port is not active, and the data must be fragmented, but the do not fragment bit flag is on. So let's actually hit the bottom two. The indicated protocol or port is not active. So let's sit on that for a moment. So the way this works from a OSI model perspective, we're looking at layer 4, and layer 4 ties into layer 5 through the session layer, and then goes up into the application for the presentation and the application. Now, let's say, for instance, from a hypothetical speaking, that I open my PuTTY session to my home router. And on my home router, I have SSH enabled, and that allows me to securely connect to the router from outside of my home and inside of my home. Well, in the situation that you could run into here, if I have a situation where I have data going back and forth between two endpoints, and I want to be able to connect to my router through SSH. Well, in order for SSH to work, the process itself has to be running. Now, the server, or in this case the router, would have to be running the SSH process and be listening on port 22, which is the SSH port. Well, that's great, but now if I go and I disable telnet, as I say, if I tell the VTY lines, don't accept telnet traffic in. If you accept telnet traffic comes in, I want you to go ahead and block it. And if that's the case, okay, fine. Now, what's actually interesting here is if I go to my server, or if I pull up PuTTY and I type in my default gateway IP address, and I point that to port 23, but the SSH service, it's not going to work. So, and because the port number is wrong. The service is right, the port number is wrong. But if I say, let's point it to port 22, but tell it to use the SSH, or the telnet service, what's going to end up happening is the PuTTY will be trying to speak telnet to the SSH listening port, but when the router receives that traffic in, the TCP connection to the port 22, he's going to look at that, and the protocol is going to come into play and say, well, wait a minute, I'm not speaking telnet. I'm going to go ahead and drop you. And then the connection will get terminated. So that's one of those situations that can come into play. Now, the process ID on, for instance, I'm a Windows guy. You know, no disrespect to Mac or Linux or any of those platforms. I just know I'm familiar with Windows. I've been working on it all of my life. I feel comfortable working with it. That's one of those situations where if the one thing that I find very interesting is people that like to do their IPSLA, their service level agreement, where they like to ping an IP address. If I can get a ping back, I know it's good. Like, okay. My argument is I disagree. I agree, but I disagree. I agree that the device, the IP, can be reached, but that does not mean that the service that you're trying to use on that server is operational. So you could do an HTTP GET, where you go out and what you're doing is you're actually hitting port 80, and you're saying, I want you to send me some information back. Maybe you get a 200 OK, or maybe you get a 404. Maybe there's an issue. That is going to be an indication of whether or not the HTTP port and the HTTP service, very, very, very important here, are operational. If that is the case, perfect, great, hallelujah, we can move forward with our day. If not, I have to go back and I have to dig into it. Now, services on any platform do get hung up from time to time. So if I have to go in there and reset a service, excuse me, sorry about that, then so be it. I have to go reset the service and get that process up and running again. If it requires a reboot of the platform, so be it. I handle that as it comes across. That is the key thing here. The messages you're getting back can be telltale as to what the problem might be, but they also could be a completely fabricated facade for an issue that might be deeper. So for those of you that are, and I fall in this boat as well, so I'm going to go ahead and shoot myself in the foot, that are big on just using ICMP Echo as a good enough method to determine next hop. I'm okay with that if I'm just pinging a router, right? If I'm just pinging a router, I'm okay with that. But if I have to have an IPSLA instance in place for a service that I have to guarantee uptime for, I'm going to go a little bit more, I'm going to dig deeper into the protocol stack and I'm going to want to get it. I want to hit on port 80, and I want to get an HTTP GET message back. So if I do a GET and I get a 200 OK back, I'm okay with that. Then I can go forward and handle my day. But if I don't get that 200 OK, if I get a 404 or some other message back that's HTTP related, then I'm going to that traffic is not going to pass, and therefore that route won't get installed. Those are situations that need to be understood. And as we're moving forward, that'll become more and more obvious as we get into like Wireshark and things like that. So, but I'll digress off the unreachable. I just wanted to make sure that to explain to you that there's more to it than just, you know, a message coming back saying, hey, you can't reach it. And for those of you that are interested, you have the ICMP, you have the echo, and you have the echo reply. Now, the difference between the two is you send the echo out and you get an echo reply back. If echo reply, they're two different messages, two completely different messages. I believe, and don't quote me here, I believe it's type 0 code 3 and type 0 code 0 are the differentiators. So type 0 code 3 I believe is echo, and type 0 code 0 I believe is echo reply, or the other way around. So, or some very close variation of that. Now then we have ICMP Redirect. Redirect results request data packet be sent to an alternative route. ICMP Redirect is a mechanism for routers to convey routing information to hosts. They manage the message informs a host to update its routing information to send packets to an alternative route. So what does this mean? And by the way, the ICMP Redirect is only valid on link local communication, which means that if I have a default gateway pointing towards R1, let's say I am PC1, I need to get to R1. So let me go ahead and just draw this out real quick and explain how this concept kind of works. It's actually very straightforward. And as far as, to my knowledge, the only platform, the only manufacturer out there that will indicate to you through a message that this is a problem is Macintosh. So if you have like a MacBook Pro, a friend of mine, actually quite a few years ago, so the way that this is actually going to work out for us here, folks, is, go ahead and grab my pen, is we have a situation here where we have destination 1, we have destination 2, and we have R1 and we have R2, but this is the default gateway, and we have PC1. We have a situation here where we have a LAN segment that is shared amongst these guys, and maybe this is HSRP or something along those lines. The first hop redundancy protocol is really irrelevant, but if I go this way for everything, but I want to get to destination 1, that means that I have to send a message back towards the receiver or the sender. I have to send a message back stating, hey, you know what? Where you're trying to go is not behind me. So if the destination is behind R1, but I'm trying to get to destination 1, but that means I have to send an ICMP redirect to say, you know what? You need to go this way to get where you got to go, and that's going to be the update to where you've got to set that information up. I believe, don't quote me on this, but I believe there is an information update sent back on a per use case situation. So you'll get an update back in, and I'm not sure if that's like a gratuitous ARP that says, you know what, if you want to go to destination X, use this particular next hop and MAC address. I don't think it works quite to that manner, but there is a redirect that says, okay, go back this direction. But that's basically the idea behind that. So if you're trying to get to a particular destination, use this path to get there. So how that actually updates the local routing table on the computer, I really don't know. I'm not even sure if there is one, or if there's an ICMP redirect all the time, or or if there's an actual route that's added to the routing table of the local computer. I honestly have no idea, but that's just a general idea behind it. So a situation like that does occur, but it needs to be understood, obviously. The next one we're going to take a look at is IPv4 Operations. So you have the type field. This is Copied fragments is set to 1. 0 is not copied, 1 bit in size if it is. So you have the option class, which is 2 bits in size. 0 is control, 2 is debug. And you're going to have a 0 and a 1. 0 is obviously a 0, a 1 is going to be the 2. The option number is 5 bits in size. You have the length is 1 byte and indicates the size of the option. Now, if we get into the data is the data is the data that's sent with the option. So if you get into the IPv4 options itself, you get into some very specific ones here. Now, the way that this actually breaks out is I actually will have to pull up a web page and break this down, but you get a type 0 code 1 option 1, something along, and it's something that breakdown, but let me go pull up that web page for you. So the way this works out is you have a 0011, which is no operation. Then as you go through here, you get several other options here. So if we were to compare these two to what we've got going on and pull up the web page, go ahead and bring this off to the side here. What you're going to end up getting here is a 001, which is no operation, which is the first one here. 001 is no operation. 0 let's see here. Is it even in here? Some of these are kind of hit or miss. But these are the option headers that you have available to you, and they get they vary as we go along. But the way that you would break these out is understanding the correlation to what it is you're trying to convey. So, for instance, and they're not always spot on. 0 to 11. Like I said, some of these they're code values that'll let you understand what it is they're trying to convey. But these are, let's say they have a record route, which is 07. And then they have a strict source, so 09. And obviously not every one of these is recorded, but that just gives you an idea of how this would actually play out. So if you were to go to the iana.org/assignments IP parameters.html, this is going to be able to give you some values that you're going to be able to look at. But beyond that, that's pretty much what gives you that flexibility of how to break that piece down. But that's basically how you would go about doing that. And then we get extension headers. So the extension headers are a fixed size of the IP header. And one of the things that they do is it's 40 bytes in size, and it lets you know what's coming. So known as the extension header, there can be a next hop in the first extension field. Keeps going until the upper layer flag is seen to go up the OSI model. And this will delineate all the possible options that may be used. So the idea behind this one is to let you know what you need to worry about as you're going through the forwarding of the data. That's the idea behind the extension header. The IPv4 fragmentation. When a router receives a packet, it examines the destination address and determines the outgoing interface to use, and that interface is MTU. If the packet's size is bigger than the MTU, and the do not fragment bit in the packet's header is set to 0, which means do not, or go ahead and fragment the packet, the router divides the packet into segments. This segment is what they refer to as fragmentation. And the size of the segment of each segment is the MTU minus the IP header, which, so between 20 and 60 bytes overall drop for MTU. And the router puts each segment into its own packet, and that is what they call fragmentation. So like for instance, MTU on Ethernet is 1500. And if I get a packet of 1660, I need to go ahead and I need to take 160 bytes and drop that down. And it's going to be one packet of 1500, one packet of 160. Now, if I was to manipulate that packet and figure out how to get it smaller through some sort of compression or what have you, I'd be able to get that extra little bit of data in there. But that's one of those cases that you might be able to work with. But that If you set the do not fragment bit or put that to a value of 1, you're going to drop the packet, because then it's trying to send 1660 bytes through a 1500 MTU lane, and there's just not enough space available. You're trying to fit, you're trying to put a square peg in a round hole, and it doesn't fit. It's simply going to be too much. You could sit there and try to work with it, but you're going to have to do something in order to make that packet smaller. You could increase the MTU, and that would allow it to go through, or you can manipulate the packet and go from there. Now, moving forward, we're going to go ahead and take a look at the IPv6 fragmentation. A packet containing a fragment of an original or larger packet consists of two parts. You have the unfragmentable part of the packet, which is the same for all fragments, and the piece of the fragmentable part of the original packet identified by the fragment offset. The unfragmentable part of the packet consists of a fixed header and some extension headers of the original packet. All extension headers up to and including the routing extension header, or else the hop-by-hop extension header. If neither extension headers are present, the unfragmentable part is just the fixed header. So what it's basically saying, and my interpretation of what it does, is if you're going out there and letting it, and you're having to fragment, it's going to have to add some additional information. And that information is going to let it know that there's additional fragments coming. So that's basically how you could interpret that. We're going to take a look at that when we actually get into how this stuff works. I don't usually cover too much on the fragmentation piece, but there's a lot of good documentation out there, and I'll point you to some of that stuff you can look at. We have the TTL, or time to live, which is a mechanism that limits the lifetime of data in a computer or network. The TTL may be implemented as a counter or a timestamp attached to or embedded in the data. Once the time span has elapsed, the data is discarded. TTL prevents a data packet from circulating indefinitely. The TTL field is an 8-bit field. In the IPv4 header, it is the 9th octet of 20, and in the IPv6 header, it is the 8th octet of 40. The way the TTL field decrements is it starts at 255, and then as it goes out 255 hops, it decrements 255, 254, 253, etc. The one thing that comes into play here is when you deal with BGP, external BGP more specifically, which we will be taking a pretty hardcore look at once we get into some of the more nitty-gritty details, is that the eBGP TTL value is a value of 1. So if you are trying to peer with another router that is eBGP as well, and that router is more than one hop away, you actually have to adjust the TTL value of the TCP header in the BGP header, in the BGP packet, I should say, to let it know how far it's going to go. The next one we're going to take a look at here is going to be the IPMTU. And the IPMTU is kind of unique, and it needs to be kind of differentiated between MTU and IPMTU. So MTU is the maximum transmission unit, and by default, Ethernet is 1500 bytes. It is defined by a PDU, or a protocol datagram unit, and fragmentation occurs when going from a large MTU media to a lower MTU media. Jumbo frames allows the MTU to forward at a higher data rate. So basically, Jumbo MTU typically sits around 9,000 bytes. I believe the cap is 9216, and that'll allow you to send larger packets every interval. So instead of being limited to 1500 bytes, you'll be able to send 9,000 bytes. This is typical on your gigabit and larger interfaces, which is a pretty much a de facto standard now. I think every platform out there, whether they label it gigabit or if they label it something else, but it forwards at a default rate of gigabit, then that'll be the indication there. But the MTU and the IPMTU are a little bit different. The MTU is, if you type it in globally, there's going to be a system MTU, which is going to be default to 1500 on most anything that runs Ethernet. Now, if you need to increase that, you can. But the capability here is when you increase that, that is going to affect the interfaces as well. So if you need to go in there and, like for instance, one of the common things that I see, and this only really happens when you're dealing with 802.1q tunneling, where you're encapsulating one 802.1q frame inside of another 802.1q frame, and you end up going above the 1500 MTU at the interface level. You're adding 4 more bytes of encapsulation, and typically this is only done inside of the service provider network, and where the service provider might be offering some sort of service to you that is layer 2 based, and maybe they are using 802.1q as in the access layer of a HVPLS design, where in the core they're doing, obviously they're doing MPLS in the core, but they're doing VPLS down to the provider edge that you peer with them on, and that's one indication that you might have to increase your MTU size. So that's one indication there. MTU overall is kind of it's kind of the wild west, and the reason I say it that way is because if you go out and your MTU is too small, you're going to fragment. If you're fragmenting, or if your MTU is larger, you won't have to fragment as much. So, for instance, when you're dealing with technologies like, for those of you that are in the enterprise, which is what this course is geared towards, it could be geared, well, the network principles specifically could be geared to any track, really, because it's it's operations of a network. But for those of you that deal with the enterprise, and it's not specifically the enterprise, you can run, and where I'm going with this is like network virtualization for VMware, NSX. They recommend that you increase the MTU in the anywhere that VXLAN encapsulation is going to be taking place to 1600 MTU, so that you're going to have the available MTU available when you need to forward the VXLAN encapsulation overhead. So they recommend an increasing of an MTU value from 1500 to 1600 to allow for those additional bytes. Sometimes you can just get away with typing in, doing jumbo frames. I'm pretty sure, from my understanding of Nexus, it does jumbo MTU by default, platform wide, and then at the interface level, you have to specify what MTU you want to have. On Catalyst switches and iOS routers, the MTU is 1500. If you need to bump that up, you can. On the virtual platforms, they don't support it, from everything that I've tested, but that's one thing that is kind of interesting about it. Now, IPMTU specifically is interface level IP forwarding MTU. It does not correlate directly back to the MTU of the system. So you can manipulate the MTU. You can say the MTU is smaller. So you type in IPMTU of 1360 or 1400. You can adjust that. So these are things that you need to keep in the back of your mind as you're doing your data forwarding and whatnot. Keep that in the back of your mind. And the last but certainly not least is new services require encapsulation in the frame. So what that means is, if you are deploying anytime you're going to be adding encapsulation to get the source traffic to the destination device, whatever method you're using to get traffic from source A to destination B, that encapsulation needs to be thought about and adjusted for automatically, because the more header space you add to your forwarding mechanism, whether that's VXLAN, whether that's OTV, whether that is IP, GRE, MPLS, it makes no difference what it is. You have to account for those additional bytes, and that is going to take away from your data MTU, your data, I should say the data segment size. Because if your MSS is 1460 or 1440, depending on how much data you're forwarding, if you add in VXLAN encapsulation and then an IPsec header and some other encapsulation, that 1440 or 1460 then drops down to 1300, 1240, 1170. It really depends on how much you have available in your data portion of your packet. These are things that you want to keep in the back of your mind as you're moving forward. Find out how much the encapsulation overhead is going to be, and you might have to send more packets, which is actually going to increase the load on the interface because you're having to send more data to send the same amount of flow. What that means is if you have a 1 gig file and you add encapsulation to get that data file from point A to point B, you're going to have to send more packets to send the same amount of data across the wire because you have shrunken down the amount of data that can be put in each packet, and therefore then you need to accommodate that additional overhead. And that's one of the things that needs to be considered. And if you don't consider that or keep that in the back of your mind, I would definitely keep that in the back of your mind. Have it as a forethought before you start deploying technologies. Ask the vendor, well, okay, what options do I have? Whether it's a service provider or what have you, maybe they can work out with you on something. So figure that out. Keep that in the back of your mind. And beyond that, guys, thank you so much for your time and your patience. I really appreciate it. And until next time, guys, take it easy.